How's it going, ladies and gentlemen? Mr. Donahue here once again, this time taking a look at determining the molecular formula from the empirical formula. Basically, how many atoms of each element are actually in this molecule. So that's our objectives, determine the molecular formula for a compound given its empirical formula and its molecular weight. These are the two things that you are going to need. You need to know the empirical formula and its molecular weight. All right, so molecular versus empirical formulas. What's the difference between those two again? Because I forget. All right, well, the empirical formula tells you the ratio between each element in a molecule, but not actually how many atoms of each element are in the molecule. It's just telling you like the ratio. So, for example, CH2O. I know there's one carbon and two hydrogens and one oxygen. That's the ratio. How many are in the actual molecule? Could be two carbons, four hydrogens, and two oxygens. I don't know. So the molecular formula will tell you exactly how many atoms of each element are in the molecule. It's telling you about the molecule. So, for example, it could be C6H12O6. Notice that C6H12O6 would simplify to CH2O, which is the empirical formula, but the actual molecule is made up of 6 carbons, 12 hydrogens, and 6 oxygens. That's its molecular formula. Okay? Sometimes they're the same thing. Sometimes the empirical formula is a molecular formula, like H2O. Can't be simplified. H2O can't be simplified anymore. It is the simplest ratio, and it is also exactly what the molecule is. It's 2 hydrogens and 1 oxygen. So sometimes they're the same thing. Carbon dioxide, same deal. So how do we determine the molecular formula? How do I figure that out? Well, first we need to determine the empirical formula if it isn't given. So if you're giving a combustion analysis kind of problem or percent composition, you got to figure out what is the empirical formula from that data. Those are whole other videos, right? So secondly, we'll need to know what the molecular weight is. Experimentally, this could be done a number of different ways. In the problem, it won't tell you how they figure it out. It'll just give it to you. Say the molecular weight is this. You have the empirical formula. Now you determine the formula weight for the empirical formula. You go, all right, if this is my empirical formula, what would its formula mass be? So then you're going to compare it to the molecular weight and see how many empirical formulas are needed to get the molecular weight. So for example, CH2O, its empirical formula is a mass of 30.02 grams per mole. If they tell you that the molecular weight is 180.12 grams per mole, then you need the equivalent of 6 empirical formulas to get to that molecular weight. And the way you're going to do that is you're going to take a look at the molecular weight, and then you're going to divide it by the empirical weight. So I'd have 180.12 divided by 30.02, and I'd get 6. So that tells me, all right, I need 6 of those empirical formulas. So now you multiply the empirical formula subscripts by how many you need to get to the molecular formula. So if it's 6, you times it by 6. You go, all right, CH2O times everything by 6. I get 6 carbons, 12 hydrogens, and 6 oxygens. So let's take a look at a problem. It says, what is the molecular formula of a compound that has an empirical formula of NO and a molecular weight of 150.05 grams per mole? So the first thing that you're going to have to do is figure out, well, what is the formula weight for NO? So I look up nitrogen. It's 14.01. And oxygen is 16.00, so I get a formula weight of 30.01. So now they tell me that the molecular formula, its mass, is actually 150.05. So I'm going to have to do this, 150.05 divided by the 30.01. So the molecular weight divided by the empirical weight, and that's going to give me 5. So I know that I'm going to have to multiply everything by 5. So I'm going to get NO, and I'm going to times those subscripts by 5. So I'm going to get N5O5. And that's it. That's how you do that. Not so bad. All right. Quinone, used in the dye industry and in photography, contains only carbon, hydrogen, and oxygen. A combustion analysis of a 0.105 gram sample yields the following data. 0.257 grams carbon dioxide, 0.0350 grams H2O. Given the molecular weight of approximately 108 grams per mole, what is its molecular formula? So the empirical formula we got to figure out first, right? And that's a whole nother video. You can look back at, it was video 3.5C, right? So look at that video for this one. You got the empirical formula of C3H2O. Don't know how that happened? Watch this video, all right? So now I got my empirical formula, and they tell me molecular weight. So I got to go, all right, well, what's the weight of the empirical formula? So I'm going to do 3 times 12.01 for carbon, and I'm going to add that to 2 times 1. 0.01 for hydrogen. I'm going to add that to 16.00 for oxygen because there's only one of them. So I get a total mass of, for the empirical formula, I wrote it down somewhere. It's right here, 54.05. So that is my empirical formula. So now to get the multiplier, figure out how many times I got to multiply it, I do 108 divided by the empirical formula's mass, 54.05, and I get almost exactly 2. So that's going to tell me I got to do 2 times that C3H2O, which is going to give me C6H4O2, and that will be my molecular formula. All right, so summarize. What information do you need to determine the molecular formula? How do you determine the molecular formula from that information? And that's it in a nutshell. All right, can you do those things? Huh? Can you do that? If not, I'll help you in class. I'll see you then. All right, okay, bye.